Hello and good day, pre-algebra. Here with you to go over math packet number 10, which is due on tax day, April 15th. So this first question here, Alexis and Vinny drove to Philly for the weekend. They decided to see some of the landmarks and needed a place to park for 3.5 hours. They see two signs advertising two different parking lots and go with the cheaper total cost. How much do they pay to park? Now, the thing I'm going to highlight here is this last question, what you're actually answering. How much do they pay to park? So you do need to find which lot is cheaper, Pat's or Paul's, but that's not your answer, okay? If Pat's parking is cheaper, you need to calculate what the cost of parking is going to be, not just write down Pat's parking, okay? If Paul's parking's cheaper, again, calculate what the cost to park is going to be. Don't just write down Paul's parking for your answer. So the difference between Pat's and Paul's parking here is that the each charge a flat rate for the first hour and then a different rate for each half hour after that. So in Pat's parking, the first hour is $8, and then it's 60 cents every half hour after the first hour. Okay. Paul's parking is cheaper for the first hour, but it's $1.25 for every half hour after the first hour. So the question here is, if you're going to be parking for 3.5 hours, is it better to go with Pat's, which is more expensive for the first hour, but cheaper for every half hour after? Or is it better to go with Paul's, which is cheaper for the first hour, but then more expensive each half hour after? So calculate the total cost of Pat's parking and Paul's parking for 3.5 hours, and then which one's cheaper? You're going to go with that one. And again, ultimately the question is, how much do you pay to park? Next one, dealing with rates here. A train leaves a train station at 1 p.m. It travels at an average rate of 60 miles per hour. A high-speed train leaves the same station an hour later. It travels at an average rate of 96 miles per hour. So eventually the second train is going to catch the first train because it is going faster. The second train follows the same route as the first one on a track that is parallel to it. In how many hours will the second train catch up with the first train? Okay, so let's just kind of it does say train leaves the train station at 1 p.m. Okay, all right. So 1 p.m. you've got train A and train B, and at this point, train A takes off, and B is still sitting there. So at 2 p.m., 1 hour later, train A has traveled 60 miles because it's going 60 miles per hour. So if it travels for 1 hour, that's a total distance of 60 miles. But train B still hasn't left yet. That's still at 0. Okay. At 3 p.m., train A has now traveled another 60 miles, so a total of 120. And train B, having left and traveling for an hour now, going at 96 miles per hour. After 1 hour, it will have gone 96 miles. Okay. At 4 p.m., train A has now gone a total of 180, 120 plus 60. And train B has traveled a total of 192, 96 plus 96. Okay, so at some point between 3 and 4 o'clock, train B catches train A, right? Because at 4 o'clock, it's gone 12 miles further, right? Whereas at 3 o'clock, it was still 24 miles behind. So what you need to figure out now is, maybe break this down into half hours. How far had train A traveled at 3:30? And if it travels 60 miles in a full hour, how far will it go in half an hour, right? Where will train B be at 3:30? If it travels 96 miles in an hour, how many miles will it travel in half an hour? And so what you're looking for is, at what time here are these two trains having traveled the exact same distance? Because that's the point where train B catches train A. So at 3 o'clock, train A has gone further. At 4 o'clock, train B has gone further. Sometime between 3 and 4, these numbers here, how far the trains traveled will be equal, and that's ultimately what you're looking for. And your answer shouldn't be, about 2 hours or less than 3 hours. It should be in exact hours and minutes, right? How many hours? It's 2 hours and 30 minutes, 2 hours and 40 minutes, right? Something like that. So you're gonna have to break these rates down a little bit. 60 miles per hour, what is that in a half an hour, quarter hour? How far does it go every 10 minutes, okay? And then something similar for train B. 5-card challenge. You're using those 5 cards to make a 2. Nothing too fancy here. You do have an ace. We love it when we have an ace because you can multiply something by 1, divide something by 1, doesn't change the value, and it's a whole different equation. So tend to a good opportunity to rack up points there with that ace. Next one, shaded area. Find the area of the entire figure and the shaded region. Show all of your work. So the area of the figure, the total figure is a rectangle. And as we've said before, the area of a rectangle is base times height. And as far as the area of that the shaded region goes, like previous packets, what we're going to need to do here is take the area of the entire figure and then subtract the area of the unshaded part, right? Because if we have the whole area and we subtract the white section, we're left with the shaded section. So that white section being a triangle, the area of a triangle equals base times height divided by 2, or 1/2 times base times height. And the base of the triangle is given to us, that's this 5 here. The height of the triangle is never diagonal side. The height of any triangle is a vertical line going from the top down to the base. And so the height of this triangle is not going to be this diagonal line here, which we don't have a measurement for. It's not going to be this diagonal line here, which we also don't have a measurement for. The height of this triangle is actually going to be this vertical line that goes from the top of the triangle down to the base. And I understand that that vertical line doesn't actually touch the base of the triangle, but it's equal, it's even to it, right? The base of the triangle being here, this vertical line comes down to a level that is equal to it. If we extended that base over to the left, the vertical line would hit it. So that is going to be your height of the triangle. And thankfully, we do have a measurement for it. It's great how that works out. So area of the shaded region there. This area of the whole thing minus the area of the white section. Now we've got our pattern blocks. Again, dealing with squares, and so similar to the last several now packets that we've had, the total column, okay, that pattern should be hopefully getting easier to find. We've got one total block in the first figure, and that one block is yellow. The rest of these are all 0. We have 9 total blocks in the second figure. Again, that one yellow, and the rest of them, the other 8, are pink. No blue and no red. In the third figure, we have 25 total blocks there. Again, the one yellow. We have 8 pink. And here's where it might start to get a little bit more tedious just to count them up. And so we can kind of think about this almost as like an equation, you know? We know the total has to be 25. We know there's 1 yellow. We know there are 8 pink. We know there are 0 red. So what's our missing number to make this equation true so that it equals 25, right? Well, 1 plus 8 is 9, plus 16 plus 0 equals 25. So there are 16 blue blocks in the figure. And you can kind of use this method to answer the other ones too. In figure 4, there are 49 total blocks. If you are not seeing this pattern for the total block column here, 1, 9, 25, 49, hopefully these numbers are starting to stand out to you a little bit. They are perfect squares. and they are the odd perfect squares. But you can, these, well, 1 by 1 square here, 3 by 3 square there, 5 by 5, 7 by 7. Our next one's a 9 by 9, right? Our squares continue to increase their side lengths by 2, which is why we get these odd perfect squares as a pattern for the total blocks column. But there's still 1 yellow, still 8 pink, still 16 blue. What's our missing number here to get to 49? That ends up being 24. Okay. And now in figure 5, which has a total block count of 81, we are back to adding yellow again. So pink doesn't change, blue doesn't change, red doesn't change. What's our missing value for the yellow? And again, we can use an equation here. 8 and 16 make 24, plus 24 is 48, and then 33. Ooh, that took longer than it probably should have to subtract 81 and 48. But it's spring break, so give me a break. Okay, so you can kind of, knowing that each number changes, or each color, there's only one color that changes in each figure. We can fill in yellow for the next one here. It's not blue's turn to change. It's not red's turn to change. We can get the total block count by following our odd perfect square pattern, and then we can just fill in that pink one there for how many pink ones there will be. So your job is to complete the table up to the 9th figure. So you can skip these last 3 if you want to do them, great, but I'm only going to be grading up to the 9th figure. Moving on, next page, we've got a triangular prism, and first up, to draw a net of the figure and label its sides. So we want to look at, what shapes make this 3-dimensional figure. Well, we've got 3 rectangles that kind of go around the sides here. You got the bottom rectangle and the 2 on the sides, and then 2 triangles that make up the ends. So 5 total surfaces here. The 2 rectangles on the sides are the same dimension. The rectangle on the bottom is a different dimension. Okay, so your 3 rectangles, 2 are the same size, 1 is larger, and then your triangles that make up the ends are the same size. And knowing that the volume is 960 cubic inches, I'm asking for the surface area. So this is what we did in class. We said, well, okay, we know that the volume for a rectangular prism is base times width times height divided by 2. That's the formula for it. For this particular triangular prism, we know the volume is 960. Which means that if the volume is equal to base times width times height divided by 2, and the volume of this prism is 960, well, that means that 960 is equal to the base times the width times the height divided by 2. And we have 2 of those 3 values for the base, the width, and the height. If I rewrite this, plugging in the values that we know, the base of this is 12. The width of this is what we don't know. That's our x. And the height of this is 8. Remember, the height is never that diagonal side, that 10. Okay? You need that to find the surface area because that 10 is a dimension of that rectangles, the 2 on the side there, but it's not the height of the prism. And that's divided by 2. Okay? And so we talked about, well, all right, what value for x, what value for the width is going to make this volume true, is going to make this formula work. 12 times what times 8, when we divide that by 2, is equal to 960. That's what you're solving for. And once you get that value, you can plug that number in for the width of the prism, and you can go to work on finding the surface area. You have now drawn the net here. Okay, you can plug that value in, find the area of each surface, and then add them all together. That's going to be your total surface area. But this equation is where you need to start here, solving for x. Then we come across our magnificent 7. Your job is to complete 3 of these 7. Write the formula for volume for the shape, and then fill in the values to make that volume happen. You've got a rectangular prism here, a cube here, which means that the base width and height all have to be the same to equal 1,331. You've got a triangular prism. We just talked about that one. The formula for the volume for this is base times width times height divided by 2. So you're looking for values for base, width, and height that when you multiply them together actually equal 140, right? This is something that some folks are kind of missing when they write these values in. You want the base, the width, and the height to multiply to be 140, because when you divide that by 2 per the formula, you get the final volume of 70, right? Then you've got a pyramid here, you've got a cylinder, a cone, and a sphere. So 3 of those 7, you're writing the formula and then filling in the values to make the formula work for the volume. Next up, we have math exploration with Fibonacci number compositions. So we've talked about Fibonacci in the past few packets, talked about the fact that it is a pattern that is found by simply adding each number in the sequence comes from the sum of the 2 numbers before it. So 1 plus 1 equals 2, right? Then you got 1 plus 2, which equals 3. 2 plus 3 equals 5. 3 plus 5 equals 8. 5 plus 8 is 13. 8 and 13 make 21, and so on and so forth. Okay? And this Fibonacci sequence shows a lot more than you might expect in nature and art and music and mathematics. And one of the ways it shows up in mathematics is the number of compositions for a given number. And by the word compositions, we are talking about using 1s and 2s to add to make the given number. So how many ways, how many compositions are there to use 1s and 2s to make a 4? Well, we've got them listed here. You could do 1 plus 1 plus 1 plus 1, 1 plus 1 plus 2, 1 plus 2 plus 1, 2 plus 1 plus 1, and 2 plus 2. Those are the 5 ways using 1s and 2s to make a total of 4. And, you know, in the 5-card challenge, we talked about how these 3 equations or these 3 compositions here would be the same, right? Because you're just adding the same numbers just in a different order. Well, this is not the 5-card challenge, okay? Here in this exercise, they're all considered different compositions, different ways to make 4. How about to find the number of compositions for 7? How many different ways, how many different compositions are there with 1s and 2s to add to make 7? Turns out there are 21. 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1, 1 plus 1 plus 1 plus 1 plus 1 plus 2, 1 plus 1 plus 1 plus 1 plus 2 plus 1. I'm not going to go through all of them, but I want to point out here is how these compositions are written very logically. Okay. First, we start with using all 1s. And since there's all 1s, there's only one way to do that. Then we move into, let's use 1, 2. And so in each of these next several, there are 5 1s and 1, 2. But notice the position of the 2. It starts at the very end. Then we move it 1 number in, and then 1 spot over, 1 spot over, 1 spot over, until finally it's first. Okay? By doing it that way, we've guaranteed that we've covered all the different ways using 5 1s and a 2. If we just kind of went about it random and say, okay, what's a way to make a 7 using 1s and 2s? Okay, here's a way, and here's another way, and I can think of this one, right? If you just start kind of randomly writing ways down, it's easy to miss some, it's easy to repeat some, it's easy to get lost. So when you do your task, which is to write all the ways to make a 5 and then make a 6 using 1s and 2s, make sure you're doing it in a logical way. Okay, have a plan going into it, not just random. Okay, so the next question here is, well, how many ways are there, right, to make a 5 using 1s and 2s? Well, Fibonacci tells us, remember when we went back, when we did this and we did n equals 4? We knew there were 5 ways because the 5th Fibonacci number, which is 5, there are 5 ways. For n equals 7, we looked at the 8th Fibonacci number, which is 21. There are 21 ways. Okay? And that little formula is, for n equals 4, we took the 4th Fibonacci and added 1 to get the 5th one. For n equals 7, we took the 7th Fibonacci and added 1 to get the 8th. So for n equals 5, we're going to look at the 5th Fibonacci and add 1, which gives us the 6th one. You're looking for 8 ways, 8 compositions to make a 5 with 1s and 2s. And once you hit your 8 of them, you can look for any repeats, and then you can be confident that you found them all. But here's an example of where Fibonacci shows up in math in ways that you probably wouldn't expect, right? I mean, just adding 1s and 2s seems so simple. The Fibonacci sequence is a very simple pattern, but it's got these connections, these number relationships that you might not expect. And here's an example of that. So, long story short, your job is those bottom 2 there, writing those compositions for 1s and 2s to make a 5, and then to make 6. Then we end on our polyomino page. Each of the 8 polyominoes is in that figure in a specific location. They are not rotated, they're not flipped. The way they appear on the left is exactly how they appear in the figure on the right, and your job is to identify where. That wraps up packet number 10. As I said, it is due April 15th. Please consider turning it in early, especially for those who want to check that square off on their bingo board. But thanks for watching. Have a great day. Don't forget to like and subscribe.